to part 6 of Project E55 ASL, and this video is going to be about making the front suspension for the car. So basically everything I need to make to connect this chassis to these two tires, and this is going to be an extremely important part of the build because you can imagine for any car that's meant for circuit racing, a time attack car, suspension is going to be an extremely important part. So that's why in this video I'm going to be spending a lot of time to get all the suspension angles right and to make the geometry work the way I want it to work for this car. So in this video I'm going to start off by making a lot of changes to the spindles for the suspension. So I'm planning to use the same spindles from the E55 suspension, by the way, because I'm planning to keep the same brakes. So it makes a lot of sense to keep the same spindles because the brakes will bolt onto those ones. And once the mounting points of the control arms are figured on the spindles, next I'm going to be making the front part of this chassis where the control arms have to attach to the chassis. And then I'm going to be making the attachment points for the control arms and making custom control arms as well. And once all that is done, then I'm hopefully going to be able to bolt everything together. And I also know you guys had a lot of questions from the previous video about the construction of the car and about solid mounting this engine to the chassis and also the front mounts that have to go on the front of the engine. So I'm going to take some time at the end of this video to answer all your questions from the previous video. But yeah, definitely a lot to cover for this video, so let's start off by making the front suspension. Now if you guys are new to suspension geometry, I made these two previous videos explaining everything about suspension geometry and why it works the way it does. So I'll link those in the description below. This video is going to be more about actually making the suspension and achieving those angles rather than explaining the reason behind those angles. So yeah, if the content in this video doesn't make too much sense, definitely try watching those videos before watching this one, and hopefully it should explain things a lot better. This is a spindle from the E55, the one that I'm planning to use for this car, but in order to use it in that car, I'm going to have to change the location of all these ball joints and basically do a lot of cutting and welding on this in order to achieve the geometry that I want to achieve for that car. And well, the reason is that the steering geometry is pretty much determined by the location of these ball joints, like where these ball joints are attached on the spindle. That will determine all your steering angles like caster, KPI, the scrub radius, and also even your steering ratio. So by changing that, I can actually customize the whole steering geometry to work the way I want it to work in this car rather than the way it works in the E55. And just to quickly explain how the geometry works on the E55, well, that is also a double wishbone suspension. So there's a top control arm that goes over here that pivots on this ball joint, and then there's a lower control arm. Well, the lower control arm is actually split into two in this car. It's something called a virtual pivot. There's one ball joint over here, and then there's another ball joint that attaches over here that is not here right now. And the lower pivot point of the steering axis is actually a virtual pivot point this way, which is why it's called a virtual pivot. So rather than that point being somewhere over here, it's actually usually on the other side of the brake rotor. It's something that you can't achieve with just one ball joint. And the reason to do it in production cars is to achieve a negative scrub radius usually, so that they can push the steering axis much further this way and like achieve a negative scrub radius. Now in order to figure out the locations of where I want my ball joints to be placed to achieve the steering geometry that I want to achieve, what I've done is that I've just tack welded this spindle onto the scrap metal that I had just to hold it in place. And I have my tripod stand set up over there. So what I'm going to do is that I'm just going to take a picture of this without the wheel, and then I'm going to put the rotor and the wheel on just like it would go in the car. And then I'm going to merge those two pictures together and then draw the steering axis through that image, and that will hopefully tell me where I want my ball joints to be placed, like where I have to attach my ball joints in order to achieve the steering geometry that I want to achieve. After this, I mounted my camera on the tripod stand, and the first image I took was with this ruler at the back. This is just so that I could see the measurements. And after that, I put the brake rotor on, and then I put the wheel on, and I bolted everything together just so that everything would be in its proper place like it would be in the car. Then after that, I took this image, and I took this image, and I merged these two images together, which gave me this image. After that, I drew this blue line through the center of the tire, which was going to be the center line of the tire. And I drew this red line, which was 5 centimeters away from the center line of the tire, which was what I was planning my target scrub radius to be. And then I drew this yellow line, which was going to be my steering axis. Like in order to meet that scrub radius, I would have had to place my steering axis somewhere over here. And once I had that figured, I could figure out the placement for my two ball joints, which is going to be the two red circles. So my ball joints, or the center point of the ball joints, should be placed at those two locations in order to achieve this geometry. And because I had that ruler at the back, now I could actually see the actual location of the top ball joint where I needed to move it in order to achieve this scrub radius. Now I'll explain a bit later in the video why I went with this geometry, which is actually quite a lot different than the geometry that the E55 had. So after this, I cut off the top mounting point of the ball joint for the upper control arm. This was because I was planning to reuse the same attachment point, but just relocate it to the place I needed to place it at. To make sure I positioned the mounting point for the ball joint at the correct position according to where I wanted to place it at, I just used some more scrap metal and I clamped it to the wheel hub, and I also clamped that mounting point to this position, and I made sure that the measurements were right. And once I had all the measurements figured and I knew everything was in the right place, I just figured out where I needed to cut this and cut the spindle at in order to weld these two things together. And then after that I did some more angle grinding and then cut the spindle off. Now for welding this ball joint mounting point on its new location, what I've done is that you can see the way I've cut it is that I've left like these edges over here so I can fill in the welds, so like the weld can actually fill in between this gap. That's just to guarantee that it's a thick weld and it will have the appropriate strength. So I'll need to apply many layers of welding, not just one, probably 3 or 4 layers of welding to fill all this gap up. First I'm going to be heating it up with the propane torch just to get everything up to temperature to give the welder a better chance to like actually penetrate through the metal. And then the way I'm going to weld it is that I'm going to apply one layer at the top, then one layer at the bottom, then one layer at the top again, and basically go back and forth. That's just to like make sure that this thing doesn't warp too much towards one side. So after that I just heated everything with the propane torch for a few minutes just to get some temperature into it. And after that I applied the weld. It was initially a little difficult to get the weld started because I guess the metal was still a little cold, but after I got some heat into it, it was pretty easy to weld the whole thing. So here's a look at the weld after it's done, and I think I applied 4 or 5 layers of welds like to fill the gap up completely, and I've gone like slightly over it, like the weld is coming above the surface, which is fine, it's just for a bit of extra strength. And same with the underside, I've also gone really thick on that, just to give it a bit of extra strength. But the weld does look pretty good, like the weld definitely did penetrate like deep within the surface, so it should be a really strong weld. Now next what I'm going to do is that I'm going to unbolt this whole hub assembly from this spindle and put it on the other spindle, because this thing is already clamped in the right place. And then I'm going to do the exact same thing for that one. I'm going to cut the section for that and use the same mark to align that one to that side, because the reason I'm doing it this way is that it's extremely important for your geometry on the left side and the right side to match up exactly, because if the geometry on the right side and left side is even slightly different, then the car will pull towards one side or do something funny. Removing the wheel bearing was pretty easy on this one. All I had to do was loosen that lock bolt that's on the nut using an Allen key, and then the whole nut just comes off, and then I can just slide the whole wheel bearing off from one spindle and onto the other. The only thing to be careful of while tightening this nut is that it has no torque specification. You shouldn't be tightening it too much. It's just supposed to be touching the wheel bearing so that there's no free play left. And after that I just tightened that bolt again to lock this in place. So I did the exact same thing on this spindle as I did on the other one, so just cut the top mounting point off and welded it on its new location. I had to measure everything a few times just to make sure that the measurements were exactly right, because it is really important for the measurements to be exactly the same on both sides. Here's what the spindles look like after all that cutting and welding, and now the position for the top ball joint is figured for the upper control arm. Now next what I have to do is do a lot more cutting and welding, and also make a whole lot of changes at the bottom, because I'm changing this whole like virtual pivot geometry and also the place where the steering rack attaches. The changes that I'm making is that, well, first of all, I'm just going to have one ball joint instead of 2 ball joints over here, and then my steering rack is going to be a rear mounted steering rack rather than a front mounted steering rack. So, well, in the E55 the steering rack was mounted in front of where the lower control arm attaches on the spindle, but I'm doing it the other way around. My steering rack is going to go behind this. That's just for placement, because in terms of placement, the way things work out in my car, it will work out better. And so what I'm planning to do is that I'm just going to cut all this section away, because I don't need this virtual pivot and even this ball joint. And I'm going to be welding in this new, like this flat bar, and I'm going to have to machine holes in this one. I'm going to have to machine one hole where this ball joint will connect the lower control arm ball joint, and then I'll have to machine another hole over here where the tie rod end would connect. And the distance between these 2 ball joints will determine my steering ratio, so like how many turns of the steering wheel will result in like how many degrees of my wheels moving. Before I could figure out my steering ratio, first I had to take some measurements from the steering rack that I was planning to use. Basically I had to measure how much one rotation of the steering wheel will move the tie rods. But after that was figured, I did some simple calculations to figure out how far apart I wanted my ball joints to achieve the steering ratio that I wanted to achieve. For now what I've done is that I've machined the starting point of these 3 holes. The reason it's 3 holes is because, well, this one is the place where the ball joint is going to go, this one is the place where the tie rod end ball joint is going to go, and this last hole is just to clamp this thing into the turntable. just so that I can machine this cone shape in the center. So the shape I need to machine for this center hole is like something like this. It's a cone shape. I measured these from the ball joint that I had. So it's 14 millimeters from the top, 12.4 millimeters from the bottom, and it's 16 millimeters like in total thickness. And I've done some rough calculations, and it gives me an angle of roughly 2.86 degrees. So that means I need to tilt my milling machine at like roughly 2.8 degrees to make the perfect cone shape for this ball joint to fit in this hole properly. So after that, I started off by drilling the 2 holes on the sides. And once the holes were drilled, I used them to clamp this piece onto the turntable, and then I machined that cone-shaped hole in the center. One thing to be careful of whenever machining holes for these ball joints, the angle has to be really specific. The ball joint like literally has to get stuck in the hole when you put it in. It's supposed to work this way because if the angle is wrong, then the ball joint will not get stuck in the hole properly, and it will move around over time and loosen the nut underneath. Once all that was done, then I had to add threads on the hole where the tie rod end connects. This is because the ball joint that I'm using for this, it has to be bolted into this one. Here's what the piece looks like after all the machining, and this is the cone shaped hole that is for this ball joint to go in. So this ball joint is going to go over here, and this hole is threaded now. This is for a bolt to go in. This is going to be the ball joint for the tie rod end for the steering rack. That's going to bolt right here. So the steering rack will actually pull or push this thing, which will turn the wheel. The only tricky thing about this one is going to be that this bar has to be at a slight angle. That's for the Ackerman geometry. I'm not going with the perfect Ackerman, by the way. I am going with the slight toe-in geometry, so that when I turn my wheel, my outside tire is at a greater slip angle than my inside tire. That's just going to help make the front end grip a little better. So after this, I marked and cut a whole lot more of the spindle away so I could make space for this flat bar to go in. And after that, I just had to fit this flat bar in its proper place. And I took some time after that to measure everything and make sure that the flat bar was in its proper place, because it's extremely important to get these angles right. Even if these angles are slightly off, like a degree off or something, you'll definitely feel it in the car. The car wouldn't drive properly, or it wouldn't grip properly. So it's definitely worth taking the extra time and measuring all these angles a few times before welding this in place, because once it's welded in place, it's going to be really difficult after that to change anything. Here's a look at the spindles after everything is done. After the welding, I have given them a quick paint just to make sure that they don't start getting rusted over time. So here's a look at the flat bar underneath, and these are the welds that I did. Again, really thick welds. By the way, I have done this before, like I have welded spindles and also axles before actually, so I know for sure that these welds are going to be strong enough. I actually also did a test weld and tried breaking it off with a hammer, and yeah, it does turn out really strong, especially for a lightweight car like this. These are definitely going to be strong enough. So now that I have the location of my ball joints figured, next what I have to do is I have to make the front part of the chassis where the control arms are going to attach onto, and then after that I'm going to be making the control arms and then bolting everything together. So there are a few more angles that are involved in that too. So the angles for like how the control arms have to go, which determines the roll center and pitch center. Also talking a bit about these ball joints, why I went with these ones. So these ball joints were originally, like this was the original ball joint used for the upper control arm in the E55, but I've used the same one for the lower control arm as well. The reason I didn't keep the original lower control arm ball joints was because they were really heavy and they were really big. I did the calculations for like how much strength I would require for something for this car, since it's a much lighter car, and assuming that these ball joints have the same strength as M14 ball joints, which they should have judging by the size, they should be good for taking this car up to 4 Gs around corners, which is more than enough. I don't think this car will go to 4 Gs in the corners unless I put it on Formula 1 tires or something. So safe enough to say these ball joints are good enough for the application, and it saves me quite a bit of weight over the original ball joints that the E55 had. And talking about weight, another benefit of all these changes is that now the spindles are extremely light. So originally these spindles weighed 5.5 kilograms, and now I've lowered the weight down to 3.5 kilograms. So that's a weight saving of 2 kilograms each side, and that's unsprung mass, so that should be pretty significant. Not to mention all the weight that I'll save in the control arms and the ball joints and everything, so pretty significant weight saving. So after this, I made the front part of the chassis, the part where the control arms for the suspension have to attach onto. Now, I didn't film making this front part in too much detail because it's pretty much just a repeat of part 4 when I was making the tube steel chassis, so just notching the tubes and putting them in their proper places. So if you want to see more of that, you can watch part 4. That's all about making the tube steel chassis. Just trying not to cover the same things that I've covered in previous videos, just to avoid the videos from getting too long. And once the front part of the chassis was done, I lowered the chassis down to its final ride height. And after this, I used some tubes to position the tires exactly where they needed to go according to the design. And once that was done, I took some measurements and I found out exactly where the ball joints on the spindles lined up with the chassis. And then I went back to the design and I updated the positions of the ball joints in the designs, and I used that to figure out how I needed to place the control arms and where the control arms needed to attach on the chassis in order to provide the proper roll center and pitch center for the car. After this, I started off by making the attachment points for the lower control arms, where the lower control arms had to bolt to the chassis. For this I used square tubing and plasma cut it in a certain shape, just like I did with the engine mounts actually. This was just to keep everything really light. They didn't end up being the best looking attachment points, but they were really light and they're of the appropriate strength. So after that, all I had to do was take a few measurements and place these attachment points exactly where they had to go according to the design. And after that, I had to do some angle grinding and cut these shapes out of sheet metal. This was to form the bolting points where the ball joints and the spindles actually have to bolt to the lower control arm. So now I have the attachment points for my lower control arms figured. So the lower control arm is going to mount on these two ball joints. And I have left a bit of play in this, so I've made the hole slightly bigger. That's just so that I can adjust my lower control arm. To get the final position of the wheel right, I can adjust it a few millimeters either side. And I've also put these plates on the ball joint. So basically next all I have to do is just weld tubes onto this one that are going to go from this plate onto these ball joints over here. And that is literally just going to be my lower control arm then. Talking about the tubes that I'm using for the lower control arm, I'm going to be going with these ones. These are again fairly thin tubes, again the thinnest possible size I can use for the lower control arm, just to save as much weight as possible, and also for aerodynamic reasons, because there's going to be no body panels around the front suspension. The front suspension is going to be open for this car, and in fact there is a front diffuser, or a front wing you can call it, that is going to go right over here. So the airflow that the front wing sucks from underneath the car is going to go through this region and then exit from the side of the car somewhere over there. So it is extremely important not to disturb this airflow too much. That's why I've gone with the thinnest possible tubes that I could go with to make this work. Oval tubes might have been the best option for this, but I couldn't find oval tubes, so round tubes is probably the second best option. So yeah, after that I just cut the tubes to the appropriate length, and then welded a cap on one side so they could be threaded onto the ball joints. And then after that I just screwed these two tubes onto the ball joints where they had to go, and then tack welded these onto the other ball joint, the ball joint for the spindle. And once everything was tack welded together, I just unbolted the whole thing and took it off just to complete all the welds. I had to be really careful with these welds not to put too much heat into the ball joint, so what I was doing was I would apply a bit of weld and then cool the ball joint down in some water, just to make sure that the grease or the rubber inside the ball joint doesn't get damaged by the heat. Once everything was done with the lower control arm, next I had to move to the upper control arm, so I started off by making the attachment points for the upper control arm. For this one I just started off with the rectangle tube and just drilled holes in it and cut it off with an angle grinder, because the rocker or the cantilever for the pushrod suspension is going to attach onto this rod as well. So that's why I used a rectangle bar rather than just using two attachment points. And after that it was just the same process as making the lower control arm, but following the measurements for the upper control arm this time. And here's what everything looks like after the control arms are mounted and most of everything is done. I still need to finish up on the welding on this top mounting point. Also I need to add some sheet metal in here to reinforce this part. This is a pretty important part of the suspension, because what you'll later see in the next part is that a rocker or the cantilever for the pushrod suspension has to go on this part. That's all going to be coming for the next part. For now, what I want to talk about is the geometry that I went with and why I chose to go with this geometry and why I think it will be suitable for this car. So starting off by the changes that I made to the spindles. So the biggest difference between the geometry of the E55 and the geometry on this car would probably be that the E55 had a negative scrub radius and now this car has a positive scrub radius. And the reason I went with that is that a negative scrub radius, it's used to cancel out any feedback in the steering wheel. So if you have torque steer or brake steer, like a negative scrub radius is usually used to cancel all those things out, so you don't feel anything in the steering wheel. And that's obviously not such a good thing to have in a track car, because whenever you're driving around the track, you do want to get as much feedback in the steering wheel as possible so you can actually control the car properly. and in case your wheels are locking up, like if you're driving without ABS and one of the wheels lock up, you do want to have feedback in the steering wheel so you can actually feel that before like the wheel actually locks up and you get a flat spot or something. That's why that was one of the problems with the E55. It gave no feedback at all in the steering wheel, so it was literally impossible to drive without ABS. So hopefully with this positive scrub radius now, it's going to make it a lot easier. The steering wheel is going to give a lot more feedback. The other major change to the spindles was that now the point where the steering rack, like the tie rod end on the steering rack attaches on the spindle, is actually much closer to the steering axis. So it's going to give a much more aggressive steering ratio. This car actually has a steering ratio of 8 degrees now, so that means that almost like one rotation of the steering wheel will result in like these tires turning fully. So that means that when I'm driving around the track, I probably wouldn't have to take my hands off the steering wheel. Like I can hold the steering wheel in the same position and drive around the entire track. So it's again going to make the car a lot easier to drive. And then also talking about the camber and caster, well, those angles are adjustable anyways in the suspension. Like you would expect in a race car suspension, that those two angles you will need to adjust from track to track, like, or different tires too. Like when you move to different tires, you would need to change your cambers accordingly, or even when you change your ride height, you would need to change your camber. So that's why I've left them adjustable. They're going to be fairly easy to adjust. The cambers can be adjusted by obviously moving these ball joints out, so that changes the angle that the tire is at. Right now I've set it to negative 2.5 degrees of camber, and the caster is 10 degrees. That's actually pretty close to what the E55 had. I was running 3 degrees of negative camber on the E55 and 10 degrees of caster. 10 degrees of caster is what it comes with. So having driven on these tires before, obviously I know what type of cambers these tires like to run at, so hopefully this should be a good starting point, and then when I actually drive the car, I can actually change the caster and camber from there and find out where it works the best. And lastly, talking about the roll center and pitch center. The roll center and pitch center, well, they're determined by the angles that your control arms are pointing at. So you might notice that these control arms aren't parallel to each other. They're actually like at a slight angle. The top control arm is more angled this way, and the lower control arm is more flatter than the upper one. Same with the angle. If you look at them this way, the upper control arm is actually going way too much towards that side, and the lower control arm is going slightly there, but it's still fairly flat. So these angles actually determine the roll center and pitch center of the car. So I've gone with a roll center of 9.3 centimeters at the front. I am going to be going slightly higher at the rear if the car turns out to be front heavy, just to fix the balance of the car. Like if the car is front heavy, obviously it's going to want to understeer, but by moving to a higher roll center at the rear, I can avoid that. That's one of those things that you can do with suspension geometry. You can actually change the understeer or oversteer. You can also do that with anti-roll bar settings, but yeah, that's another way to do it. And the pitch center is even higher. It's actually 25 centimeters. That's to avoid the car from diving down too much. And actually, I'll mount my camera on the tripod stand and I'll show you how this wheel moves around when I actually move it. It's actually pretty cool to see because you'll see some of these things happening. So let me just move the wheel by hand and show you guys some of the cool features of this geometry. So like this is how the suspension will move up and down. So the first thing you'll probably notice about the suspension is that when it moves up and down, you might notice that the spindle also rotates slightly this way when the suspension moves up, and that is the thing that gives the suspension the anti-dive geometry. So you can imagine that when the brakes are applied and the spindle is trying to rotate that way because of that braking force, it will also have a slight force pushing downwards because of that rotation, and that is what helps cancel out the dive on the front end. So like when you go on the brakes, this geometry actually prevents the nose from diving down too much under braking, which is actually an extremely important thing to have in downforce cars, because in downforce cars you don't want the nose to be diving down too much, especially in high-speed corners, because what that does is that when your nose dives down, you gain a tremendous amount of downforce at the front and you lose downforce at the rear, because your rear diffuser can actually stall if your nose dives down too much. Also showing you guys the way the wheel turns, like when the wheel turns to either sides. Now you can see that well, the way the wheel turns, the first thing you'll notice is that it's gaining camber when it changes direction. Like when it turns this way, you can imagine that this is going to be the outside tire on the corner, so it has to camber that way, and you can see that it is cambering that way. And when it turns the other way, it cambers the other way, so it is going to be a heavy steering wheel, that's for sure. It's even hard to turn it by hand. So obviously it's cambering the right way whichever way you turn. That's because of the caster angle, and the more I increase the caster angle, the more it will like camber more when the wheel turns. That's something that I'll be fine-tuning even more when I go on the track. So when I actually drive this car and I check the tire temperatures, how the tires are doing, whether the outside of the tires is being used more, the inside of the tires is being used more, then I'll adjust the caster and the camber and get them to a point where like the tire is being optimized the best, and that's obviously going to give the best possible lap times then. So that is going to be everything for this video. I know I still haven't even finished the suspension for this side, but I'm going to leave that for the next weekend probably. I'm running a little out of time right now. But I do want to answer some of your questions that you guys had from the previous video about solid mounting this engine and why I chose to go with this construction. Well, first of all, this is not really an uncommon way of constructing race cars. Most race cars, ever since like the 1970s, I believe, Formula 1 cars have used this way of construction, like solid mounting the engine and transmission to the chassis and like using them as a stress member to like actually support the chassis rather than the chassis supporting the engine. So the benefit of this construction is that, well, first of all, just to explain the construction, there's 4 bolting points that you guys saw in the previous video, part 5 of E55 ASL. So these 4 bolting points that hold the bell housing adapter to the chassis, and then 2 bolting points at the back where the transmission is connected, and then there's going to be 4 bolting points that are not here right now that are also going to link the front of this engine to this front part of the chassis. So what this construction will do is that you can imagine that when the engine is bolted to the chassis on all these different points, you can imagine that when that part of the chassis tries to twist because of the suspension, like because of the car going over bumps or whatever it goes over that makes the chassis twist, you can imagine that it will have to twist the entire engine along with it. And the engine is obviously a big block of aluminum, so it doesn't really want to twist. It's actually a really solid block. It doesn't twist at all actually, and that's why it's such a common way used in racing, because it's a much better idea of like tying the engine with the chassis rather than just mounting the engine on a piece of rubber where it is not contributing to any strength in the chassis. The reason they've used rubber mounts in road cars is just to isolate a bit of noise and a bit of vibration. But even solid mounting the engine, I have tried it before in 2 projects actually. One was a 4-cylinder Honda engine and the other one was a V8 Toyota 1UZ, and both of those engines didn't really have an awful lot of vibration. But anyways, yeah, getting to like the front mounts, that's the other question a lot of people had, how I plan to mount the front of the engine to the chassis. So the thing is that usually for Formula 1 cars or for most race cars, they will attach the engines with the valve covers. So they have specially designed valve covers that are actually much stronger than this magnesium one, and they have bolting points that bolt directly back to the carbon fiber monocoque that they usually have. But what I'm going to do is that since my valve covers are magnesium and they're really weak, they're definitely not strong enough to mount anything to. So the thing that I'm doing later is that I'm removing this supercharger and I'm going with a custom intake manifold. So I'm going to be making a custom intake manifold which is going to extend much further than it should extend, and then at the front of the intake manifold I'm going to have this structure that is going to like go all the way till the corners of the chassis and then attach over here. And for the bolting points at the bottom that are going to attach to these corners of the chassis, I'm going to have to modify my lower oil pan. I am thinking of taking the lower oil pan off later for possibly a dry sump system. I haven't decided on that yet. When I have the oil sump off, I will be modifying the oil sump and making it a lot longer, like reinforcing it and also adding bolting points on it so that it can be bolted to the chassis over there. So those are going to be my 4 bolting points on the front of the engine. But yeah, that's to come for way later. So that is going to be everything about this video. Let me know if you guys have any questions about the suspension geometry or any other questions about the construction of the car, and I can try to answer those in the next video probably. The next video is going to be about the push rod suspension and figuring out the steering system, actually mounting that steering rack to the suspension, and yeah, just doing more work on the suspension pretty much. But yeah, really happy with the way things are taking shape. Hopefully this car will have a ton of mechanical grip with this new suspension. But yeah, that's everything for now. Thanks a lot for watching. Hopefully see you guys in the next one.